Good morning to all of you. I am Tanu from BSc Chemistry Honors second year. Today we are discussing about carboxylic acid. Now let's start. At first, introduction. Organic compounds containing carboxylic as the functional group are called carboxylic acid. The COOH group, which itself is made up of carbonyl group and a hydroxyl group, is called carboxyl group. Carboxylic acid may be aliphatic or aromatic according as the COOH group is attached to an alkyl group or an aryl group. The general formula are written as RC double bond O single bond OH. Aliphatic or aromatic carboxylic acid are further classified as mono, di, tri and polycarboxylic acids according as they contain 1, 2, 3 or many carboxyl group in their respective molecules. A large number of carboxylic acids are found in nature. Actually, higher members of aliphatic carboxylic acids containing 12 to 18 carbon atoms occur in natural fats as triesters of glycerol. Therefore, these are called fatty acids. Carboxylic acids are not important as such, but they also serve as starting materials for preparing a number of other important compounds such as acid chlorides, anhydrides, ethers, and amides. Therefore, in this unit, we will discuss in some detail the chemistry of monocarboxylic acids. Electronic structure of the carboxyl group. In the carboxylic group, the carbon atom is attached to two oxygen atoms, one by a double bond and the other by a single bond, which in turn is linked to a hydrogen atom by a single bond. The remaining free valency of the carbon atom of the carboxylic group is satisfied by a hydrogen atom or an alkyl group. Thus, the electronic structure of carboxylic acid is. Electron and neutron diffraction studies have revealed that COOH group is a planar species. This suggests that the carbon atom and the two oxygen atoms are sp2 hybridized. The two sp2 hybridized orbitals of the carboxyl carbon atom overlap with one sp2 hybridized orbital of each oxygen atom, while the third sp2 hybridized orbital of carbon overlaps with either a s orbital of hydrogen atom or a sp3 hybridized orbital of carbon atom of the alkyl group to form 3 sigma bonds. Each of the two oxygen atom and the carbon atom are left with one unhybridized p orbital which is perpendicular to the sigma bonding skeleton. All these three p orbitals being parallel overlap to form a sigma bond which is partly delocalized between carbon and oxygen atom on one side and carbon and oxygen of the OH atom of the other side. In other words, RCOOH may be represented as a resonance hybrid of the following two canonical structures. As a result, the CO single bond length in carboxylic acid is shorter than the normal carbon-oxygen single bond in alcohols and ethers. Second, C double bond O double bond length in carboxylic acid is slightly longer than normal C double bond O bond in aldehydes and ketones. Comparisons of resonance structures of carbonyl group and carboxyl group. As discussed in Unit 6.1, a carbonyl group has two resonance structures. However, for a carboxyl group, three resonance structures can be written. In both structures, the carbon atoms and the two oxygen atoms have 8 electrons in their respective valence shells, while in structure B, the carbon atoms has only 6 electrons. Therefore, structure B is less stable than structure C. In other words, the two important resonance structures of carboxyl group are structure A and C. In both these structures, carboxyl carbon is electrically neutral. However, in case of aldehydes and ketones, only one structure, that is the electrical neutral. As a result, the carboxyl carbon of the resonance hybrid is less positive and hence electrophilic than the carbonyl carbon of aldehydes and ketones. However, it may be noted that like carbonyl group, carboxyl group is also polar due to the resonance structure that are shown above. Nomenclature of carboxyl group. First, aliphatic acids. The aliphatic monocarboxylic acid are commonly called fatty acids because their higher members such as palmitic acid, stearic acid, oleic acid, etc. are obtained by hydrolysis of oils and fats in which they occur as their triacyl glycerides. The aliphatic monocarboxylic acid are named by the following two systems. First, common or trivial system. Second, IUPAC names. Common or trivial system. The common name of aliphatic monocarboxylic acids are derived from the Greek or Latin name of the source, that is plant or animal product from which they were first isolated. The irradiation resulting from an ant bite is due to formic acid, which was first prepared by distillation of red ants, that is acetic acid, and butyric acid, and caprolic and capric acid are some other examples. IUPAC names. The IUPAC names of the saturated monocarboxylic acid is alkanoic acid, that is, their names are derived by replacing the terminal E from the name of the corresponding straight chain alkane by the suffix oic acid, and hence they are called as alkanoic acids. Like HCOOH is known as common name formic acid, and the corresponding alkane is methane, or IUPAC name is methanoic acid. The substituted and branched chain acids are named as derivative of the longest straight chain. The position of the substituents are indicated by alpha, beta, gamma, delta, and so on, with the carbon adjacent to the carboxyl group being designated as alpha as the common system. However, in the IUPAC system, the position of the substituents are indicated by Arabic numerals, with the carboxyl group being numbered 1 as shown. The IUPAC name of some branched chains or substituted acids are given. The corresponding names are given in the parentheses. Second is aromatic acids. The simplest aromatic monocarboxylic acid is benzoic acid. The IUPAC name of the substituted acids are derived by prefixing the name of the substituent to the name of the parent chain, that is benzoic acid, and its position indicated by an Arabic numeral, with the carbon atom carrying the COOH being numbered 1, or by prefixes ortho, meta, and para. Methods of formation. Some of the principal general methods of preparation of carboxylic acid and described below. First, from primary alcohols and aldehydes. The primary alcohols and aldehydes are readily oxidized to the corresponding carboxylic acid with common oxidizing agents such as KMnO4 in neutral, acidic, or alkaline media, or by K2Cr2O7 and CrO3 in acidic medium. Oxidation with K2Cr2O7 and CrO3 in acidic media often gives some amount of esters. Therefore, oxidation with KMnO4 is neutral or alkaline medium is preferred. Under these conditions, potassium salt of the acid is first formed, which upon treatment with dilute H2SO4 gives carboxylic acid. Aldehydes are easily oxidized to the corresponding carboxylic acid even with mild oxidizing agents such as Tollens reagent. Second, from alkyl benzenes and alkenes. Aromatic acids are obtained by the oxidation of alkyl benzenes with a number of oxidizing agents such as acidic or alkaline potassium permanganate, acidified potassium dichromate, or even dilute HNO3. During these oxidations, the aromatic nucleus remains intact, but the side chain is oxidized to a carboxylic group irrespective of the length of the chain. The carboxylic group formed is always attached to the aromatic ring, and the position of the carboxylic group indicates the position of the original side chain in the starting arene. Third, from nitriles. Hydrolysis of nitriles with a boiling mineral acid or an alkali yields the corresponding carboxylic acids. Alkyne and alkyl cyanides needed for the purpose are themselves prepared from alkyl and alkyl halides by treatment with KCN, while aryl cyanides are prepared from the corresponding diazonium salts by treatment with KCN in presence of CuCN. Thus, the hydrolysis of nitriles provides a useful method for the preparation of carboxylic acid containing one carbon atom more than the original alcohol or the alkyl or aralkyl or the aryl halide. Mechanism. First, acid hydrolysis of nitriles occur by the following mechanism. Second, basic hydrolysis of nitriles, and at last we get the carboxylate ion. Fourth is hydrolysis of acid chloride, anhydrides, esters, and amides. All these acid derivatives upon hydrolysis gives the corresponding carboxylic acids. There is of hydrolysis however, varies markedly and follows the order. Acid chloride is greater than acid anhydride, it is greater than esters, it is greater than amides. While acetyl chloride reacts instantly with water, acetic anhydrides react rather slowly. Esters and amides, on the other hand, can be hydrolyzed only by heating them with either a mineral acid or an alkali. While esters are hydrolyzed easily, amides react at a much slower rate. Although hydrolysis of acid chlorides and anhydrides is seldom used as a practical method for preparing carboxylic acid, the hydrolysis of two naturally occurring classes of acid derivatives, that is oils and fats and proteins, have been used for preparation of certain acids. Fifth, carbonation of Grignard reagent and organolithium compound. Carboxylic acids can be prepared by the action of Grignard reagent or organolithium compounds on crushed dry ice suspended in ether. The addition product thus formed on decomposition with a mineral acid gives the carboxylic acid. Both the nitrile and the Grignard reagent, the organolithium compound methods, are useful for converting an alkyl or aryl halide to the carboxylic acid having one carbon atom more than that present in the alkyl and the aryl halide. Sixth, malonic ester and acetoacetic ester synthesis. Mono and dialkyl derivatives of acetic acid can be easily prepared by malonic ester and acetoacetic ester synthesis as described below. Malonic ester synthesis. Diethyl malonate, commonly called malonic ester, is an active methylene compound. The acidic hydrogen atom of the active methylene group can be abstracted by a strong base, such as a metallic sodium or sodium ethoxide, to form sodio-malonic ester. This, upon treatment with an alkyl halide, undergo alkylation to form monoalkyl derivative of malonic esters. The monoalkyl malonic ester still has one acidic hydrogen and hence can similarly be converted into dialkyl malonic ester. The mono and dialkyl malonic esters thus formed upon hydrolysis with aqueous NaOH or KOH followed by acidification gives the corresponding mono and dialkyl malonic acids. These acids, upon subsequent heating, undergo decarboxylation to form the corresponding mono and dialkyl derivative of acetic acid. By using suitable alkyl halides, malonic ester synthesis can be used to prepare any acid. To illustrate this method, suppose we want to synthesize N-valeric acid. This acid may be regarded as N-propyl derivative of acetic acid, that is CH3CH2CH2CH2COOH. In order to synthesize this acid, sodio-malonic ester should be first converted into N-propyl malonic ester by reaction with N-propyl bromide, and the N-propyl malonic ester thus obtained by hydrolysis and subsequent decarboxylation should give the desired acid as shown. First, malonic ester react with NaOC2H5, give rise to sodio-malonic ester, and then react with alkyl halide, give rise to N-propyl malonic ester, then react with sodium hydroxide, and then react with an acid, and at last heating we get the N-valeric acid. Second, acetoacetic ester synthesis. Like malonic ester, acetoacetic ester can also be used to synthesize any mono or dialkyl derivative of acetic acid. For this purpose, the acetoacetic ester is first converted into its sodium salt by treatment with metallic sodium or sodium ethoxide. Alkylation of sodio-acetoacetic ester with an alkyl halide gives the corresponding monoalkyl acetoacetic ester. This process may be repeated to form dialkyl acetoacetic ester as shown. The mono and dialkyl acetoacetic ester thus obtained upon acid hydrolysis with concentrated aqueous or ethanolic KOH followed by acidification with a dilute mineral acid gives a molecule of acetic acid and a molecule of alkyl acetic acid or dialkyl acetic acid. For illustration, consider the synthesis of 2-methylbutanoic acid as described below. Seventh, hydrolysis of 1,1,1-trihalides. Carboxylic acid can also be prepared by the hydrolysis of 1,1,1-trihalides with an alkali. Eighth is oxidation of methyl ketones. Methyl ketones on treatment with a solution of sodium hypohalite, that is NaOCl, NaOBr or NaOI, undergo haloform reaction to give the corresponding haloform along with the sodium salts of carboxylic acid containing one carbon atom less than their respective parent ketones. The sodium salts of carboxylic acid on acidification gives the corresponding acid. For example, ninth, Baeyer-Villiger oxidation. Baeyer-Villiger's oxidation of ketones with peracids gives esters, which upon hydrolysis gives the corresponding carboxylic acids. 10th, Arndt-Istad homologation. The conversion of an acid into its next higher homologue is called homologation of an acid. It can be easily carried out using Arndt-Istad synthesis. It involves the following steps. The acid is first converted into acid chloride by treatment with SOCl2, which is then treated with diazomethane to form a diazoketone. On treatment with Az2O, the diazoketone undergoes Wolff rearrangement to form a ketone, which upon hydrolysis and subsequent tautomerization gives the higher homologue of the acid. 11th, from olefins. Monocarboxylic acids may be prepared by heating an alkene with carbon monoxide and steam under pressure of 573 to 673 Kelvin in the presence of a catalyst such as H3PO4. For example, from sodium alkoxide and carbon monoxide. When a suitable sodium alkoxide is heated with CO under pressure, it gives sodium salts of the carboxylic acid, which upon subsequent acidification gives the corresponding acid. Physical properties. First, smell. The first three aliphatic acid, that is formic acid, acetic acid and propioionic acid, are colorless, pungent smelling liquids. Butyric acid has odor of rancid butter. The next five acids, that is from C5 to C9, are also colorless, only liquids with somewhat unpleasant smell. But the acids with 10 or more carbon atoms are colorless, waxy solids with no distinct smell, probably due to low volatility. Most of the aromatic solids exist as colorless solid with no distinct smell. Second, solubility. Amongst the aliphatic acid, the first four acids are fairly soluble in water, while pentanoic acid and hexanoic acid are only slightly soluble. In contrast, the acids containing 7 or more carbon atoms are partially insoluble in water due to an increased proportion of the hydrocarbon part in the molecule. Benzoic acid, the simplest aromatic carboxylic acid, is nearly insoluble in cold water since the non-polar hydrocarbon part outweighed the effect of the polar carboxylic part. However, all carboxylic acid are soluble in less polar organic solvents such as benzene, ether and alcohol. The solubility of the lower members in water is due to hydrogen bonding, in which carbonyl oxygen forms hydrogen bond with the hydrogen atom of water and hydroxyl hydrogen forms hydrogen bond with oxygen atom of water. As the size of the alkyl group increases, the solubility of the acid decreases due to an increase in the hydrocarbon part of the molecule and reduced polarity. Boiling point. The boiling point of the carboxylic acid are much higher than those of hydrocarbon and somewhat higher than those of aldehyde ketone and even alcohols of comparable molecular masses. This means that carboxylic acid forms even stronger intermolecular hydrogen bond than alcohol. This may be explained as follows. First, as compared to alcohols, the OH bond in carboxylic acid is more strongly polarized due to adjacent electrons withdrawing carbonyl group. Therefore, carboxylic acid forms stronger hydrogen bond. Second, the negatively polarized oxygen atom of the carbonyl group can also form hydrogen bonds with the positively polarized hydrogen atom of the hydroxyl bond of the other molecule. The hydrogen bonds are so strong that they are not broken even in the vapor phase. In fact, in vapor phase or in aprotic solvent, most of the carboxylic acid exist as cyclic dimers in which the two molecules of the acid are held together by the two strong hydrogen bonds. Melting point. The melting point of aliphatic carboxylic acid do not show a regular pattern. The first 10 members show oscillations or alternation effect. That is, the melting point of an acid containing even number of carbon atoms is higher than the next lower. First 10 members show oscillations or alternation effect. That is, the melting point of an acid containing even number of carbon atoms is higher than the next lower and higher homologous containing odd number of carbon atoms. This may be explained as follows. It has been shown by X-ray diffraction studies that acids containing even number of carbon atoms have carboxyl and terminal methyl groups on the opposite sides of the zigzag carbon chain. As a result, they fit closely in the crystal lattice, thereby increasing intermolecular forces of attraction, resulting in higher melting point. On the other hand, carboxylic acids with odd number of carbon atoms have the carboxyl and terminal methyl group on the same side of the zigzag carbon chain. These fit poorly in the crystal lattice and hence have lower melting point. The melting points of aliphatic acids having more than 10 carbon atoms do not show the oscillations effect. The melting point and boiling point of the aromatic acids are usually higher than those of aliphatic acids of comparable molecular masses. This is possibly due to the reason that planar benzene ring in these acids can pack closely in the crystal lattice than zigzag structure of aliphatic acids. Acidity of carboxylic acids. Carboxylic acids are more acidic than alcohols and phenols but are much weaker acid than the mineral acids and sulfonic acids. In aqueous solution, the carboxylic acids ionize and exist in dynamic equilibrium between carboxylate ion and hydronium ion. According to the law of mass action, the equilibrium constant K can be expressed as K is equal to RCO negative and H3O positive divided by RCOH and into H2O. Since water is taken in large excess, its concentration remains constant. Therefore, the above equation may be written as is equal to Ka. Ka is called the dissociation constant of the acid. It varies only with the temperature for a given liquid. From the above equations, it is clear that the value of Ka is directly proportional to the concentration of H3O positive ions or simply H plus ions. Therefore, the value of Ka is a measure of the acid strength of an acid. Evidently, greater the value of Ka, greater is the tendency of the acid to ionize and hence stronger is the acid. pKa values. The numerical values of Ka of different Bronsted acids cover a range of many powers of 10. Therefore, it is sometimes more convenient to express the acid strength of an acid in terms of its pKa value, which is a negative logarithm of the equilibrium constant Ka. pKa is equal to minus log of Ka. Evidently, smaller the numerical value of pKa, stronger is the carboxylic acid. Thus, carboxylic acid with pKa is of the order 5 are much weaker acid than mineral acids. However, they are much stronger acid than phenol, while pKa of the order of 10 and alcohol with pKa of the order of 16. Thus, both Ka and pKa can be used to compare the acidic strength of different carboxylic acid. The K and pK value of some important aliphatic and aromatic acids are given. Structure of carboxylic acid and their acidic nature. Carboxylic acid may be regarded as the resonance hybrid of the structure 1 and 2. Due to the presence of positive charge, oxygen atom attracts the electron of the OH bond towards itself. As a result, the OH bond weakens and ultimately breaks to split off a proton. This is responsible for the acidic nature of the carboxylic group. After the removal of a proton, the resulting carboxylate anion is also stabilized by resonance as shown below. Thus, both carboxylic acid and the carboxylate anion are stabilized by resonance, but the resonance energy of carboxylate anion is more than that of undissociated carboxylic acid. This is due to the fact that the canonical structure 3rd and 4th for the carboxylate anion are equivalent and also do not involve separation of positive and negative charges, whereas the contributing structures 1st and 2nd for the undissociated acid are not equivalent and also involve separation of positive and negative charges. In other words, it is the greater stability of the carboxylate anion as compared to carboxylic acid which is responsible for the ionization and hence the acidic character of the carboxylic acids. Since the carboxylate anion is a resonance hybrid of two equivalent structures, therefore the negative charge is no longer localized on one or the other oxygen atom but is evenly distributed over both the oxygen atoms and the carbon atom of the carboxylate anion. As a result, each of the two oxygen atoms in the carboxylate anion is attached to the carbon atom by 1.5 bond. In other words, both the carbon-oxygen and bond length in carboxylate anion must be equal and should lie in between C single bond O and C double bond O bond lengths. On the other hand, in carboxylic acid, the two carbon-oxygen bond lengths should be different. Since one of the oxygen atom is linked to the carbon atom by a double bond whereas the other is linked by a single bond, the above conclusions are supported by X-ray and electron diffraction studies of bond length of carboxylic acids and their anions. For example, formic acid has two different carbon-oxygen bond length, that is C double bond O bond length is 1.23 angstrom, whereas C single bond O bond length is 1.36 angstrom. On the other hand, the formulate anion two carbon-oxygen bond length are equal, that is 1.27, and lie in between the values of C double bond O length is 1.23 and 1.36. Comparison of acidic character of alcohols and carboxylic acid. Both alcohols and carboxylic acids contain an OH group, but carboxylic acid are much stronger acid than alcohols. For example, acetic acid is about 10 raised to power 10 to 10 raised to power 11 times a stronger acid than ethyl alcohols. This is due to the fact that both carboxylic acid and carboxylate anion are stabilized by resonance, but neither the alcohols nor their alkoxide ions are stabilized by resonance. On the contrary, alkoxide ion is destabilized since the alkyl group has electron releasing inductive effect, and this tends to intensify the negative charge on the oxygen atom. In other words, alkoxide ions are less stable than alcohols and hence they have little or no tendency to release a proton. On the other hand, carboxylate anions are more stable than the carboxylic acid and hence they have a strong tendency to release a proton. This explains why alcohols are much weaker acid than carboxylic acid, though both contain an OH group. Comparison of acidic character of phenols and carboxylic acid. Both carboxylic acid and phenols are acidic in nature, but carboxylic acid are stronger acids than phenols. To explain this, let us consider the resonating structure of carboxylate ion and phenoxide ion. In case of phenoxide ion, structures carry a negative charge on the less electronegative carbon atom. Therefore, their contribution towards the resonance stabilization of phenoxide ion is very small and hence can be easily rejected. Let us now consider only those structures which have a negative charge on the more electronegative oxygen atom for the carboxylate ion and the structure for the phenoxide ion. The negative charge on the carboxylate ion is delocalized over two oxygen atom, while in structures third and fourth, the negative charge on oxygen atom remains localized while the electrons of the benzene ring only are delocalized. Since delocalization of benzene electrons contributes little towards the stability of phenoxide ion, therefore carboxylate ion is much more resonance stabilized than phenoxide ion. Thus, the release of a proton from carboxylic acid is much easier than from phenols. In other words, carboxylic acid are stronger acid than phenols. Effect of substituent on the acidity of carboxylic acid. First, aliphatic acids. We have just discussed above the acidity of a carboxylic acid is due to the powerful resonance stabilization of the carboxylate anion. Evidently, any factor which tends to increase the stabilization of the carboxylate anion over the carboxylic acid should increase the strength of the acid, and any factor which tends to make the anion less stable than the acid should decrease the acidity of the carboxylic acid. In the light of these arguments, it is expected that electron-releasing groups such as alkyl group would destabilize the carboxylate anion by intensifying its negative charge and hence should decrease the acidity. Conversely, electron-withdrawing groups such as halogens would stabilize the carboxylate anion relative to the carboxylic acid by dispersing its negative charge and hence should increase the acidity of the carboxylic acids. Let us now discuss briefly the effect of various substituents on the acidity of carboxylic acid. First, effect of electron donating substituents. If the non-hydroxylic hydrogen atom in formic acid is replaced by an alkyl group, the acidity of the carboxylic acid falls. For example, formic acid is about 10 times stronger acid than acetic acid. This is due to the reason that the plus I effect of the methyl group destabilizes the acetate ion relative to the formate ion by intensifying the negative charge on it. Further, since the plus I effect of the alkyl group increases in the odor, acetic acid greater than propyne, ionic acid greater than isobutyric acid greater than pirulic acid. Second, effect of electron withdrawing substituents. Substitution of an alpha hydrogen of the alkyl group by an electron withdrawing group increases the acidity of an acid. For example, chloroacetic acid is a much stronger than acetic acid. This is due to the reason that the minus I effect of the chlorine atom tends to stabilize the chloroacetate ion relative to acetate ion by dispersing the negative charge on it. Now, since the minus I effect of the halogen decrease in the order fluorine and then larger as chlorine, greater than bromine, greater than iodine, the acidity of the alpha halo acids also decrease in the same order. Thus, it is described as. Further, greater the number of electron withdrawing substituents, greater should be the dispersal of the negative charge and hence stronger will be the acid. We also know that the inductive effect decreases rapidly with distance. Thus, as the distance between the electronegative substituents and the COOH group increase, the dispersal of the negative charge of the corresponding carboxylate ion becomes less pronounced and hence the acidity decreases. B. Aromatic acids. A COOH group has minus I effect as well as plus R effect as shown. When phenyl group is directly attached to a carboxylic group, it has an overall electron donating effect, however weaker than the plus I effect of an alkyl group. As a result, unsubstituted aromatic carboxylic acid are stronger acid than unsubstituted aliphatic carboxylic acid. Thus, benzoic acid is a stronger acid than acetic acid. Further, since formic acid does not contain any alkyl group, therefore it is a stronger acid than benzoic acid. Thus, the relative acid strength of formic acid, acetic acid, benzoic acid follows the sequence: formic acid greater than benzoic acid greater than acetic acid. Effect of substituent on the acidity of aromatic acids. The nature and the position of the substituents on the benzene ring has a marked effect on the acidity of benzoic acid as shown. From the above table, we are emerged that first, electron donating substituents tends to decrease and electron attracting substituents tends to increase the acidity of substituted benzoic acid. Second, the acid weakening effect of the electron donating groups and acid strengthening effect of the electron withdrawing substituents is more pronounced at para than the meta position. Third, ortho substituted benzoic acid are usually stronger acid than benzoic acid regardless of the nature of the substituents. This is called ortho effect and is probably due to combination of steric and electronic factors. Explanation: the electron donating group tend to destabilize the carboxylate ion relative to the undissociated acid by intensifying the negative charge on the carboxylate ion. As a result, these substituents decrease the acid strength of the substituted benzoic acid relative to benzoic acid. Conversely, electron withdrawing substituents tends to stabilize the carboxylate ion relative to undissociated carboxylic acid by dispersing the negative charge on the carboxylate ion. As a result, such group increase the acid strength of the substituted benzoic acid relative to benzoic acid. Effect of the electron donating group at meta and para position. The electron donating group decreases the acidity of acids. This decrease is more than the para than the meta isomer. In other words, para isomer are weaker acid than meta isomer. This can be explained as: at the same time, they have electron withdrawing inductive effect due to higher electronegativity of the heteroatom than carbon. These two effects operate in opposite direction, whereas plus R effect tend to decrease the acidity. The minus I effect tends to increase the acidity of the substituted benzoic acid. In the para isomer, both these effects operate, but in the meta isomer, only the minus I operates, since the resonance effect cannot occur. Further, since the plus R effect outweighs the minus I effect, therefore para isomer are weaker acid than the corresponding meta isomer. Para-hydroxybenzoic acid is a weaker acid than the meta-hydroxybenzoic acid. Similarly, para-methoxybenzoic acid is a weaker acid than the meta-methoxybenzoic acid. Effect of electron withdrawing group at meta and para position. Electron withdrawing group increase Electron withdrawing group increase the acidity of the acids. This increase in acidity is however greater at para than the meta position. All the electron withdrawing groups withdraw electrons both by resonance and inductive effect. Both these effects operate in the same direction and tend to increase the acidity of the acid. In the para isomer, both these effects operate, but in the meta isomer, only the minus I effect occurs since minus R effect cannot take place. Therefore, it is reasonable that para isomer are stronger acid than meta isomer. Ortho effect. The ortho substituents have an acid strengthening effect, and this effect is unexpectedly large. Thus, ortho substituted benzoic acid are much stronger acid than their meta and para isomer, no matter whether the substituent is electron donating or electron withdrawing. This effect is called ortho effect and is probably due to the combination of steric and electronic factors. In the light of above facts, the relative acid strength of ortho and meta and para-toluene acids as compared to benzoic acid follows the sequence. Similarly, the relative strength of ortho, meta, and para-hydroxybenzoic acid relative to benzoic acid follows the sequence. Likewise, among nitrogen benzene as follows. Chemical properties. A molecule of carboxylic acid except formic acid is made up of two parts. First, an alkyl or aryl group. Second, a carboxylic group. The carboxylic group may be further considered to be made up of a carbonyl group and a hydroxyl group. Therefore, the carboxylic acid are expected to show the reaction of both these groups. However, the reactions expected of these groups are somewhat modified as a result of interaction between these groups due to their proximity. We have already discussed that the carbonyl carbon in carboxylic group is less electrophilic than the carbonyl carbon in aldehydes and ketones due to resonance. Therefore, many nucleophilic addition reactions such as formation of oximes, hydrazones, phenyl hydrazones, 2,4-dinitrophenyl hydrazones and semi-carbazones of aldehydes and ketones do not take place with carboxylic acids. From the above discussion, it follows that the reaction of carboxylic acid are characteristic of the carboxylic group and the alkyl or the aryl group and are situated under the following headings. First, reaction due to hydrogen atom of the carboxylic group. A few reactions showing the acidic character of the carboxylic acid are given below. First, reaction with metals. Carboxylic acid react with active metals like sodium, potassium, zinc, etc. to form their respective salts, liberating H2 gas. Second, reaction with carbonates and bicarbonate. Carboxylic acid decomposes carbonate and bicarbonate, producing CO2 gas. This reaction is used to detect the presence of a carboxylic group in an organic compound. Since most of the phenols do not produce effervescence with aqueous solution of NaHCO3, therefore this reaction can also be used to distinguish phenols from carboxylic acid. Third, reactions with alkalines. Carboxylic acid react with hydroxides and metallic oxide to form salts. It may however be noted that carboxylic acid are much weaker acid than mineral acids like HCl, HNO3. Therefore, salts of carboxylic acid are readily decomposed these mineral acids to regenerate carboxylic acids. Part 2. Reaction involving the OH group of carboxylic acid. The hydroxyl group of carboxylic acid, like the hydroxyl group in an alcohol, can be replaced by a number of groups such as chlorine, OR, NH2O, Cr prime to form acid chloride, esters, amides, and anhydrides respectively. These derivatives are collectively called as functional derivative of carboxylic acid. First, formation of acid chloride. Reaction with SOCl2, PCl5 or PCl3. Carboxylic acid react with the thionyl chloride, phosphorus pentachloride and phosphorus trichloride to form acid chlorides by the replacement of the OH group by the chlorine atom. In actual practice, thionyl chloride method is preferred to PCl5 or PCl3 method, since both that byproduct being gases escape into the atmosphere and the thionyl chloride being volatile can be easily removed by fractional distillation, leaving acid chloride in almost pure state. Second, formation of esters. Reaction with alcohols. When carboxylic acid are heated with alcohols in presence of H2SO4 or dry HCl gas, that is Fischer-Spear esterification, esters are formed. The reaction is reversible in nature and is known as esterification. Since esterification is an equilibrium reaction, therefore to shift the equilibrium in the forward direction, either the carboxylic acid or the alcohol is used in excess. It is usually the alcohols which is taken in excess. The yield of the equilibrium reaction can be further increased by removing water from the reaction mixture, as it is found by using a special apparatus called Dean-Stark apparatus. Mechanism of esterification has already been discussed in Unit 1st. Relative reactivities of acids and alcohols. The rate of esterification is sensitive to steric hindrance. As the number and size of the substituents around the carboxylic group or the hydroxy group in alcohols increases, the rate of esterification slows down. Third, formation of amides. Reaction with NH3. When treated with ammonia, carboxylic acid form ammonium salts which upon heating lose a molecule of water to form acid amides. Fourth, formation of anhydrides. Action of heat in presence of P2O5. When carboxylic acid are heated in presence of a strong dehydrating agents such as phosphorus pentoxide, acid anhydride are obtained by the elimination of a molecule of water from two molecules of the acids. Acid anhydrides can also be obtained by treating acid chloride with carboxylic acid in presence of pyridine as a base, or by treating acid chloride with sodium salts of the carboxylic acid. Third, reaction involving the carboxylic group as a whole. Carboxylic acid and their salts undergo a number of reactions which involve either the elimination or the decomposition of the carboxylic group. Some of these reactions are discussed below. First, decomposition or decarboxylation. First, chemical decarboxylation. Sodium salt of carboxylic acid when distilled with soda lime undergo decarboxylation to yield alkanes. Mechanism: decarboxylation occurs through intermediate formation of a carb anion which subsequently picks up a proton to form the corresponding hydrocarbon. Effect of substituents on decarboxylation. Since formation of carb anion or organosodium compound is a key step in the above reaction, therefore any factor which tends to increase the stability of the carb anion should increase the rate of decarboxylation. Thus, carboxylic acid, which contain an electronic withdrawing group such as NO2, COH, etc., at beta position with respect to the carboxylic group, readily undergo decarboxylation on heating through a six-membered cyclic transition state. B. Electronic decarboxylation. Electrolysis of aqueous solution of sodium or potassium salts of fatty acids gives alkanes. This process is called Kolbe's electrolytic reaction. At cathode, both sodium and hydrogen are present, but hydronium ions are preferentially discharged due to their lower discharge potential with respect to sodium ions, and thus hydrogen gas is evolved at the cathode. The overall Kolbe's reaction may be represented as electrolysis of sodium formate, however, yield only H2 but not an alkane. C. Decarboxylation of silver salts of carboxylic acid in presence of bromine. The silver salts of carboxylic acids on treatment with bromine in refluxing CCl4 gives alkyl या aryl bromides containing one carbon atom less than the parent acid. This reaction is called Hunt's-Decker reaction. Mechanism: the reaction occurs by free radical mechanism through intermediate formation of acyl hypobromite as shown. D. Decomposition of calcium salts of fatty acids. Dry distillation of calcium salts of fatty acids give aldehydes or ketones. For example, first, dry distillation of calcium formate gives formaldehyde. Second, dry distillation of calcium salts of an acid other than the formic acid gives a ketone. Third, dry distillation of a mixture of calcium formate and calcium salt of an acid other than formic acid gives an aldehyde other than formaldehyde. Second, reduction to alkanes. Carboxylic acid on reduction with hydroiodic acid and red phosphorus at 473 Kelvin gives alkane. B. Reduction to alcohols. Carboxylic acid are resistant to catalytic hydrogenation. However, reduction of carboxylic acid with lithium aluminium hydride or better with diborane gives primary alcohol. During the reduction, CO group of the carboxylic group is reduced to CH2. This method is used for the preparation of alcohols from acid which are directly available from natural sources. The reduction of carboxylic acid can also be brought about by the first converting them into esters and then are easily reduced to alcohols by sodium and alcohol, known as bivalent blank reduction. Fourth, reaction of the alkyl group, that is halogenation. Carboxylic acid react with chlorine or bromine in presence of small quantities of red phosphorus to give exclusively alpha chloro and alpha bromo acids. This reaction is called Hell-Wohlhard-Jalenski reaction. If more than 1 mole of chlorine or bromine is used, the second and third alpha hydrogen atoms can be successfully replaced. It may be noted that bromination exclusively occurs at the alpha position and the reaction stops after all the alpha hydrogen have been replaced by the bromine atom. In contrast, chlorination first occurs at the alpha position, and when all the alpha hydrogen have been displaced, it occurs further along the chain. Function of red phosphorus. Red phosphorus first combines with bromine to form little PBr3. This then reacts with carboxylic acid to form the corresponding acid bromide, which enolizes to a greater extent than the acid and thus bring about alpha bromination easily. Thank you.